Welcome, guys. In this video, we are going to study applied maximum minimum problems. We'll solve various applied optimization problems where our main goal is going to be to write down this function of a single variable, then use techniques from our previous lecture videos on finding global or absolute maximum and minimum values of function on open or closed intervals. So we'll need to find the value of parameters that will maximize our function. Let's start solving problems. Let's take a look at the following problem. Okay, so we have garden that is to be laid out in rectangular area and protected by a chicken wire fence. What is the largest possible area of the garden if only 100 running feet of chicken wire is available for the fence? So basically we have a garden, a rectangular area. Let's set up some parameters. Let's call this side length as x, this side length as y. Then our first constraint is that perimeter should be equal to 100 feet since the length of available wire is only 100 feet. So 2x plus y is equal to 100. So x plus y is equal to 50. All right, so this course is calculus 1, is a calculus of single variable. So we don't know how to work with functions of several variables. So our first goal is then going to be to write down the functions that will try to optimize the function for which we'll be searching for absolute maximum or minimum, to write down this function as a function of a single variable. So we want to maximize the area. Area here is defined as x multiplied by y. Now this is a function of two variables, but we can use our first constraint here. We can express y as 50 minus x, and if we replace y as 50 minus x, then we'll get 50x minus x squared. So now a is a function of a single variable, is a function of x. So now we need to find a maximum, the value of x that will maximize the area. And now first, before proceeding, our next step is to set up the interval of possible values for x. So first of all, x should be positive, and then since we only have 100 meters of running wire, x should not exceed the value of 50. So x is defined in interval from 0 to 50. Okay, now our goal is similar to the techniques that we studied in previous lecture video. We need to find absolute maximum of this function on that interval. Or rather, we need to find the value of x that will maximize this function in this interval here. So then to do that, we need to find the critical values of this function by taking first derivative. It's equal to 50 minus 2x, from which x is equal to 50, x is equal to 25, is the only critical point. It is a stationary point. Now to find absolute maximum value of this function in that interval, we need to check the value of function at point 0 at endpoints. So at point 0, it's equal to 0. At point 25, a of x is then equal to 25 multiplied by 25, so 25 squared. Now at right endpoint, at x is equal to 50, the value of our function is again equal to 0. So we see that the maximum of our functional interval from 0 to 50 is at point x is equal to 25 and is equal to 25 squared. Okay, so The steps that we did in this problem will be similar for all other problems. Let's take a look at those steps and specify them. All right, so the steps you need to take to solve applied optimization problems. First one is to draw an appropriate figure and label the quantities relevant to the problem. As we did before, we modeled our problem by drawing a plot of rectangular garden, and then we gave name for our parameters. Those were the side lengths of our rectangle. Then next step is to find formula for the quantity to be maximized or minimized. So in previous problem, the quantity that we need to maximize is area of this rectangular region, which is equal to x multiplied by y. So using the conditions stated in the problem to eliminate variables, express the quantity to be maximized or minimized as function of one variable. So we said that we don't know how to work with functions of several variables yet, so we need to use constraints. Our constraint was that perimeter was equal to 100, and use that constraint to express a as a function of a single variable, let's say x or y. Then find the interval of possible values for this variable from the physical restrictions in the problem. Physical restrictions in that problem was that x should be positive and perimeter was equal to 50. So x was defined only in interval from 0 to 50. And next step, final step, if applicable, use the techniques of preceding sections to obtain the maximum, minimum, or obtain absolute maximum or minimum. Okay, so those steps will be similar for all the problems that we are going to solve in that video. All right, so we have an open box that is to be made from 16 by 30-inch piece of cardboard by cutting out squares of equal sizes from the four corners and bending up the sides. What size should the squares be to obtain a box with the largest volume? So we have rectangular region of cardboard and we cut out the squares of side lengths x at the corners. Then we lift those up such that we have the following cube or box that is open at the top. And we need to find the value of x that will maximize the volume of that box. So let's start by writing down the functions that we need to maximize. So that function is a function for volume. Let's take a look at our cube. Then this side length is equal to 30 minus 2x. Since we have this side length on original rectangular region as being equal to 30, then if we cut out those parts, this side length is now going to be 30 minus 2x. And similarly, other side length is going to be 16 minus 2x. And since we are lifting those upwards and this side length is equal to x, the height of our cubic box is going to be equal to x. So this is a function that we need to maximize, function for volume. Now let's find a range of possible values for x. First, x should be positive. And second, we cannot cut out x's such that it will exceed this side length, the smallest side length. The smallest side length is equal to 16, and we have a constraint that 2x should be less or equal than 16. So our next constraint is that x is less or equal than 8. So the range of possible values for x are in the interval from 0 to 8. So we need to find absolute maximum of this function on that closed interval. To do that, we are going to find critical points by taking derivative. I already found the derivative here. It's equal to 4x minus 12, 3x minus 10. So critical points are x is equal to 12 and x is equal to 10 over 3. So these are two stationary points. And as we can see, x is equal to 12 is outside of our range of possible values for x. So this point isn't interesting to us. And inside of that closed interval, then from 0 to 8, we have only critical point, only stationary point at x is equal to 10 over 30. And what we are going to do, we are going to calculate the value function at endpoints at 0 and at 8. And the value of that function at its only stationary point at 10 over 3, it's equal to 726. So value of x is equal to 10 over 3 will maximize volume, and the maximum volume is equal to 726. We could also skip doing that analysis, since from our previous lecture, we have a theorem that if a function has on a single relative extrema inside of open or closed intervals, so if there is only one relative extrema point, then that relative extrema point will be absolute extrema point on that interval. And in that closed interval, we have only single critical point, x is equal to 10 over 3, and this is a point of relative maximum. To see that, let's take a look at the value of v prime. On interval from 0 to 8, we have this critical point at 10 over 3. And the other critical point is at 12, but it's outside of this interval. So if we substitute minus infinity, this is negative, this is negative. So our function is going to be positive here, positive up to 10 over 3. And at 10 over 3, multiplicity is 1. So odd multiplicity, so the sign will change, minus, and then it's going to decrease, and after 12 it will be positive, but we don't care what happens after 12. The only thing we care about is that function is increasing up to 0.10 over 3, and then it's decreasing after 0.10 over 3. So at point x is equal to 10 over 3, our function has a relative maximum. Now, this relative maximum is the only relative extrema point. So this is relative maximum on interval from 0 to 8. And there are no relative extrema points in that interval, meaning that at x 10 over 3, which is relative maximum point, we'll also have absolute maximum point. So you don't have to calculate the values at endpoints if you have single relative extrema point inside of your interval. Okay, guys, so the two problems that we have solved previously, they were problems where we needed to find the absolute maximum or minimum value of a function only on finite and closed interval. Now let's take a look at the following problem where involving interval will not be finite and closed. So it can be open and infinite. So a closed cylindrical can is to hold 1 liter, 1000 cubic centimeters of liquid. How should we choose the height and radius to minimize the amount of material needed to manufacture the can? So we have a closed cylindrical can. Then we need to find the value of the values of parameters r and h such that it will be able to hold 1 liter of liquid, and its surface area, in other words, amount of material needed to manufacture this can, is going to be minimized. So we need to write down the function for the surface area of this can. If we set height to be h and other parameter radius to be equal to r, then its surface area can be decomposed into the following two parts. One is going to be a rectangular sheet of metal with side lengths of h and 2 pi rh, and area of it is equal to 2 pi rh. And then we'll also have a couple of circles that encloses the can at top and bottom. Area of those are equal to pi r squared, and we have two of these, so that will be 2 pi r squared. Okay, so we have a function, but right now we cannot proceed since this is a function of two variables. So we need to use our constraints to make this as a function of one variable. We know that cylindrical can is to hold 1 liter of liquid, meaning that its volume should be equal to 1000. So its volume of cylinder is equal to pi r squared, by the area at the base multiplied by height h. And this should be equal to 1000. Then we can replace either r or h in our function here to make this as a function of a single variable. So let's express h in terms of r. So it's equal to 1000 over pi r squared. Okay, so now s replacing h will have 2000. Pi's will cancel out. R cubed r cubed, not r cubed, I'm sorry. So that will be r over r squared. So 2000 over r, 2000 over r plus 2 pi r squared. Okay, now let's define the range of possible values for our parameter r. So r cannot be equal to 0, then since then we are going to have a can of 0 volume. So r should be positive and should not be equal to 0. So r is defined in interval from 0 to plus infinity, an open interval from 0 to plus infinity. Okay, now we are going to find critical points of that function, and we are going to find absolute minimum value of this function on that interval. Okay, so derivative of our function s is then equal to minus 2000 over r squared plus 4 pi r. Bringing that to common denominator, we'll have 4 pi r cubed minus 2000 divided over r squared. So here we see that we have two critical points. At r is equal to 0, we have a point where our function is non-differentiable, but we are not interested in that point since it's outside of our interval because our interval here is open. Second critical point is when 4 pi r cubed is equal to 2000. That will give us the value of r that is equal to cubic root of 1000 over 2 pi. So this is 10 over cubic root of 2 pi. And it's approximately equal to 5.4. So now let's study our function here and let's show that this critical point, the stationary point, which is approximately equal to 5.4, is only a relative extrema point inside of our interval, and meaning that if it is only a relative extrema point, it's going to be absolute extrema point in that interval. So we need to show that this point is point where our function reaches its minimum. So to do that, we are going to study the sign of S prime. We have a critical point at 0, but we'll not care about this one. Then we have critical point at 5.4. Okay, now multiplicity here is odd. Multiplicity here is odd, meaning that the sign over this will alternate. Now, if you substitute plus infinity here, that will be positive, that will be 0. So this is plus. And multiplicity here is odd, minus, and we don't care what happens after this point. But if we are interested, multiplicity here is even, so the sign will not change. But we don't care about this point since our interval here is open and it's outside of this interval. So critical point 5.4. So our function is decreasing, then increasing, meaning that at point 4 we have relative minimum. Since 5.4 is the only relative extrema point inside of this open interval, then it's going to be an absolute minimum. Outside minimum point of this functional interval from 0 to plus infinity. Okay, so the dimensions that will minimize the surface area are value of r that is equal to 5.4 and the value of h that is going to be equal to 100 over pi over 5.4 squared. And on quizzes and midterms and next midterm exam, guys, I might ask you to find the value of parameters that will maximize or minimize your function, and will also might ask what is the absolute maximum or minimum value of this function. So we should be able to calculate both. All right, guys, now this will conclude our lecture on applied maximum minimum problems.